In this lecture, we will be exploring the notion of diagonalizability of normal operators and self-adjoint operators in the right setting. From the lectures in week 8, if you recall, linear operator is said to be diagonalizable if we can get hold of a basis of the vector space consisting of eigenvectors of T. We will show that in the right setting, normal operators and self-adjoint operators are diagonalizable. This is what is classically known as the spectral theorem. We will be concluding this course by giving a proof of the spectral theorem for these operators. Okay, so let's begin. So let me just write the heading spectral theorem. So suppose before we enter into the statement of the spectral theorem, so if T be a linear operator on an inner product space, be a linear operator on a finite dimensional inner product space, and suppose we have an orthonormal basis, and suppose beta is an orthonormal basis consisting of eigenvectors of T. Suppose we are in this setup. So observe that what we are demanding is that what is given to us is that T is a diagonalizable linear operator. Not only that, the eigenvectors are orthonormal to each other. But then recall that the matrix of T with respect to beta will be a diagonal matrix. What have we checked about diagonal matrices? We have seen that diagonal matrices are normal. The product of the diagonal matrix and its conjugate transpose will be equal to the product of the conjugate transpose of the matrix and the matrix itself. So, which is a normal matrix. And by one of the theorems we have proved earlier, if a linear operator has a matrix representation with respect to some orthonormal basis which will give us a normal matrix, then the linear operator itself is normal. This helps us conclude that T is itself a normal operator. So what we have observed is that if there is a diagonalizable matrix with a basis consisting of orthonormal vectors of eigenvectors, then the linear operator T is normal. Our spectral theorem is in some sense a converse to this. What our spectral theorem says is that this is true in general. Spectral theorem says the following: if we start off with complex inner product space, finite dimensional complex inner product space V, and if T is a linear operator on V which is normal, then there exists an orthonormal basis of V consisting of eigenvectors of T. In particular, our linear operator T is diagonalizable. Spectral theorem for normal operators. So the setup has already been laid out for you. We are in a complex inner product space, finite dimensional complex inner product space, and T is a normal operator on V. So let V be a finite dimensional complex inner product space. And T in L of V be a normal operator. It's linear transformation from V to itself be a normal operator. Then the spectral theorem tells us that then there exists an orthonormal basis of V consisting of eigenvectors of T. So, the spectral theorem tells us that not only is T diagonalizable, but the basis of eigenvectors of T, they are also orthonormal. Alright, so let us give a proof of this. Before giving a proof of the spectral theorem, let us look at what we have actually observed right now. What we have just seen is, in the previous observation here was telling us that if you have a linear operator which has which satisfies the condition that V has an orthonormal basis consisting of eigenvectors of T, then T is necessarily a normal operator. And the spectral theorem tells us that if T is normal, then V contains an orthonormal basis consisting of eigenvectors. So, in a complex inner product space, normal operators are precisely those operators which satisfies the condition that V has a orthonormal basis consisting of eigenvectors of T. Okay, so let us give a proof of the spectral theorem. The proof is by induction. Induction on what? Induction on dimension of V. So, this is a very finite dimensional inner product space proof that we are going to give. So, when, which let us call it to be equal to n. So, if n is equal to 1, what does that mean? That means that let V be a basis of capital V which has norm 1 such that length of V is equal to 1. So, since capital V has dimension 1, this particular vector will form a basis, and because there are no other vectors, it is by default an orthonormal basis. And we know that TV is a scalar multiple of V, since V is a one dimensional vector space, and that implies that V is an eigenvector of T, and thus there exists an orthonormal basis consisting of eigenvectors of T. So, the case when n is equal to 1, there is nothing to prove. Okay, let us now assume that n is greater than 1. So, by induction hypothesis, let us assume that the theorem has been proved for up to n minus 1. By induction hypothesis, assume the theorem to be proved for up to n minus 1. So, we will prove that when dimension of V is equal to n, then the spectral theorem is satisfied, or spectral theorem is true. Okay, so the induction hypothesis tells us that for any linear operator which is a normal operator on a vector space which is a complex inner product space of dimension less than n up to n minus 1, there exists an orthonormal basis consisting of eigenvectors. So, to prove for n, let us consider the characteristic polynomial of our given operator. So, let f of lambda be the characteristic polynomial. So, recall that if you pick any basis and look at the matrix of the operator T corresponding to that basis, let us call that matrix A, then compute the characteristic polynomial of this A. Then that is we can call that the characteristic polynomial of our given operator, because you change the basis, any change of basis will give you a similar matrix to our to this matrix A, and therefore the characteristic polynomial will not change. So, the characteristic polynomial of a given operator is a well defined polynomial with coefficients from the field of scalars. In this case, it's a complex inner product space, and therefore f of lambda is a polynomial with coefficients in the complex numbers. Now, by the fundamental theorem of algebra, our polynomial splits into linear factors, and we can write f of lambda to be equal to lambda minus say lambda 1 times lambda minus lambda 2 up to say lambda minus lambda n, where n is the dimension of our given vector space. These lambda 1, lambda 2 up to lambda n are complex numbers. So, the characteristic polynomial splits over the field of complex numbers. What do we know about the roots of the characteristic polynomial? We know that the roots of the characteristic polynomials are precisely the eigenvalues of our given linear operator t. Notice that there is no demand on these lambda i's to be distinct. That has never been a demand even in the cases we were discussing earlier. But then certainly it splits. That's the only thing we know, and the roots turn out to be the eigenvalues. So, in particular, lambda 1 is an eigenvalue. So, let V1 be an eigenvector of lambda 1, eigenvector of lambda 1 of t corresponding to lambda 1. That means, what does it mean? It means that corresponding to lambda 1, i.e. tv1 is equal to, okay, moreover, we may assume that the length of v1 is 1. We may assume that length of v1 is equal to 1. Why can we do that? Because suppose we started off with a v1 which did not have length v1 equal to 1, we will look at the scalar multiple of 1 by length of v1 times v1. Now, the good thing about the vector v1 is that it is non-zero because it is an eigenvector. Therefore, length of v1 to begin with was not 0, and therefore 1 by length of v1 makes sense. And now, if you look at the length of v1 by the length of v1, that should have unit length, and that is why we may assume without loss of generality that the length of v1 is equal to 1 to begin with. And t1 is equal to lambda 1 v1 will be the identity which states that v1 is an eigenvector of t corresponding to lambda 1. But t is a normal operator. T is normal implies, we have already proved this, that if lambda 1 is an eigenvalue of t, then lambda 1 bar will be an eigenvalue of t star in the case of finite dimensional inner product spaces. And in the case of when t is a normal operator, we have proved more. We have proved that the eigenvector corresponding to lambda 1 of t will be the same as the eigenvector of t star corresponding to lambda 1 bar. So, we will, because t is normal, we also have that the adjoint of t v1 is equal to lambda 1 bar times v1. So, this is good because now what we will do is we will define W to be the vector subspace of V, which is defined as the span of V1. Notice that notice that W is invariant under both T and T star, Why? Because V1 is lambda V1 and T star V1 is lambda 1 bar v1, which both of which belong to capital W itself. So, this is a vector subspace which is invariant under both T and T star. Now, consider the orthogonal complement of W. So, consider the orthogonal complement of W given by W orthogonal. So, the first observation which we have already seen in one sense is to notice that W orthogonal is invariant under both T and T star. We have already seen a proof of this, but nevertheless it is quite a useful thing to see even once more. So, let W be a vector in the orthogonal complement of capital W. What does this mean? This means that inner product of V with V1 is equal to 0. Notice that the moment we have this condition, inner product of V1 with W is 0, that means that W is in the orthogonal complement of capital W, because any vector in capital W will be a scalar multiple of V1, so it will be C times V1, and W inner product with V1 is 0 would imply that W inner product with C times V1 is also 0. So this is exactly the characterization of W being in the orthogonal complement of capital W. Okay, but this is right. So let's consider TW, and we would like to see that this is also in the orthogonal complement of capital W, and in order to do that we should check that the inner product of TW with V1 is 0. But what is this? This is the inner product of W with T star V1, and V1 is an eigenvector of T star, which is the inner product of W with lambda 1 bar times V1, which is equal to lambda 1 times the inner product of W with V1, which we just observed is equal to lambda 1 times 0, which is equal to 0. So this implies that TW is in the orthogonal complement of capital W. Similarly, maybe it's just one line, T star W inner product with V1 is equal to the inner product of W with TV1, which is equal to lambda 1 bar times the inner product of W with V1, which is equal to 0, which implies that T star W is also in the orthogonal complement of W. So what does this say? This means that hence E restricted to orthogonal complement of W is a linear map from the orthogonal complement of W to itself. Similarly, T star restricted to the orthogonal complement of W is also a linear map from the orthogonal complement of W to itself. Also, notice that inner product of T restricted to W orthogonal of W comma W1 comma W2, this is equal to the inner product of T W1 W2, which is equal to the inner product of W1 T star W2, which is the same as W1 T star restricted to W orthogonal W2 for all W1 W2 in the orthogonal complement of W. So what this says is that the restriction map of T star is the adjoint of the restriction map of T. So that is good, because this tells us, okay, so let me just note that for you. T restricted to the orthogonal complement of W star is precisely going to be equal to T star restricted to the orthogonal complement of W. Hence, T restricted to W orthogonal times T star restricted to orthogonal, which is equal to T star restricted to the orthogonal complement of W, is the same as T star T or maybe I should just say that this of W is equal to this of W, which is the same as this of W, which is the same as T star restricted to W orthogonal of T star T restricted to W orthogonal of W, which tells us that T restricted to the orthogonal complement of W is normal. Now we are in good shape, because W orthogonal is a vector subspace of V which has dimension n minus 1. Notice that the orthogonal complement of there was a version of the dimension theorem for the orthogonal complement. You should go back and check. This is just going to be equal to n minus 1, because the dimension of W was equal to 1. And by our induction hypothesis, notice that T restricted to W is a normal linear operator on a vector complex inner product space of dimension n minus 1. The inner product is just the one borrowed from V. So by induction, there exists an orthonormal basis, let's call it beta prime, of W orthogonal such that consisting of eigenvectors of T restricted to orthogonal complement of W. So, the first thing to notice is that beta prime is a subset of W orthogonal, and in particular beta prime is a subset of V as well. Hence, beta prime is an orthonormal set in capital V. In the inner product space V, this is an orthonormal set. They are orthogonal and has length 1. Now, let us look at beta to be equal to V1 union beta prime. So, if beta prime was say V2, V3 up to Vn, beta is just now going to be V1, V2 up to Vn. And notice that beta is also an orthonormal set. The reason being that each of the beta elements in beta prime are vectors in W orthogonal, and in particular they are orthogonal to our vector V1, and therefore this is a collection of mutually pairwise orthogonal vectors, and we already started off with length of V1 being equal to 1. So, beta in particular is an orthonormal set in capital V, and notice that each of them are eigenvectors consisting of eigenvectors of T, because V1 to begin with was an eigenvector corresponding to lambda 1, eigenvectors of T. Okay, one observation here is that an eigenvector of consisting of eigenvectors of T restricted to W orthogonal, this implies that beta prime consists of eigenvectors of T. Why is that the case? Because if T restricted to W orthogonal of W is equal to some lambda lambda j times, let me just write it down, since T restricted to W, or rather for W in beta prime, TW is just equal to T restricted to the orthogonal complement of W acting on W. Now, this is just going to be some lambda j times W, and therefore W is an eigenvector that I just noted. That would imply that each of the beta prime consists of eigenvectors of T as well. Well, eigenvectors of T restricted to W orthogonal is just going to be eigenvectors of T as well. So, that is the simple observation here, and therefore this beta will have an orthonormal set consisting of eigenvectors of T. But what is the size of beta? The size of beta is equal to n minus 1 plus 1, which is equal to n, because beta prime has n minus 1 vectors, right? After all, W orthogonal had dimension n minus 1, and they are all, that's an orthonormal set. Hence, beta is a set of size n which is linearly independent. And what do we know about a linearly independent set of size n in a dimension n vector space? We know that it is a basis. This gives that beta is a basis of V, and we are done with the proof. So, we have just proved that in a complex inner product space, the normal operator is always diagonalizable. Not only is it diagonalizable, we also have a basis of eigenvectors which is orthonormal. Okay, that's pretty nice. So, there are a couple of observations, couple of remarks here. The first one is to observe that this is a statement which has complex inner product space put into the very hypothesis of the statement, because if you consider T, so remark, consider T from R2 to R2. This is a real inner product space given by t of x comma y to be equal to, let's look at the example we had given in one of the previous lectures. We will just use the same example here. Was it x minus y? Yes. T, okay, minus y comma x. Let's look at this particular example. Minus of y comma x. So what was the characteristic polynomial? To do that, let's look at what was t beta beta, where beta was the standard basis. If you recall, this is just going to be equal to 0, 1, minus 1, 0, and hence f of lambda is just going to be equal to lambda square plus 1. And if you notice, this is a polynomial which doesn't split over real numbers, does not split over R. So the fundamental theorem of algebra is, it just tells us that it splits over the complex numbers. This particular polynomial, however, doesn't split over R, and hence this is a linear operator which doesn't even have eigenvalues, t from R2 to R2. So it is a normal operator which doesn't even have eigenvalues. So there is no question of getting hold of a basis consisting of eigenvectors. So hence T is an example of a normal operator on a real inner product space which is not diagonalizable. Let's look at, however, the case when, let's say, call it S. So let's look at example now. SB from C2 to C2. A very similar map let's define. S of, instead of x comma y, let's use some z comma w, and this will be what, minus of w comma z, just like the map we have defined here. And let's see what will be the matrix of S with respect to beta. So let beta be equal to the ordered basis consisting of 1 0 and 0 1. Notice that this is in C2. So all complex numbers, you look at the span with respect to all the field of scalars being complex numbers. Okay, so what is S beta beta? As was observed earlier, this is just going to be equal to 0 comma 1 in the first column and minus 1 comma 0, and therefore f of lambda is equal to lambda square plus 1, which is lambda minus I times lambda plus I, where I is the square root of minus 1. Therefore, there are two eigen values here. Hence, lambda 1 is equal to I and lambda 2 is equal to minus I are the eigenvalues. So, notice that the splitting is to be expected by the fundamental theorem of algebra. Here in this case it was easy, hence I could write it down very easily. Lambda 1, the roots are going to be the eigenvalues of our linear operator. So, I and minus I are the eigenvalues of t, of S rather. That means S of, let's look at what the eigenvectors will be at, for eigenvector of Z of I. Eigenvector, one of the eigenvectors of I will be something of this type, I times Z comma W, but this we know is equal to minus of W comma Z. Yes, that means this is equal, that means this gives us that IZ is equal to minus of W. So this would imply that when Z times, the first one can be put as 1, if Z is 1, W would be minus I. This is an eigenvector of E corresponding to I, eigenvalue lambda 1 equal to I. How about minus I? If S of Z comma W is equal to minus of I times Z comma W, this would imply that I times Z is equal to W, and minus of I times W is equal to Z, which makes sense. and therefore z is equal to 1 comma I is an eigenvector of minus I. So what would be an orthonormal basis? So we have already seen that in the case of a normal operator, the eigenvalues corresponding to distinct eigenvectors corresponding to distinct eigenvalues should be orthonormal. So in particular, this is orthonormal. You can check it straightforward in a straightforward manner using the inner product space as well. All right. So I'm sorry. Right. So beta being equal to 1 comma minus 1, after orthonormalizing it will be 1 by root 2 times 1 comma minus I, and 1 by root 2 times 1 comma I is an orthonormal set consisting of orthonormal basis rather consisting of eigenvectors of S. Let's call it beta prime. We already called beta as the standard basis of S. And what is going to be S beta prime? Beta prime, this is just going to be equal to I comma 0 0 comma minus I. All right, so that's an example of that's this example illustrates that in the case of complex inner product spaces, normal operators are diagonalizable, whereas in the case of real inner product spaces, normal operators need not be diagonalizable. The example we just gave illustrates that. However, if you notice, our first example was an example of a normal operator which was not a self-adjoint operator. So of course, all self-adjoint operators are normal operators, and therefore, if you consider self-adjoint operators over complex inner product spaces by the spectral theorem for normal operators, we know that that is also a diagonalizable linear operator. But we can ask more. What can we at all say anything about self-adjoint operators on real inner product spaces? And the answer turns out to be yes. We can say something more, and that is going to be the content of the spectral theorem for the self-adjoint linear operators. So this is going to be the spectral theorem of self-adjoint operators. So now let us look at a real inner product space. We have already addressed the case of a complex inner product space, right? Self-adjoint operators are normal, and as I was just mentioning, because of the spectral theorem for normal operators, we also have a spectral theorem for self-adjoint operators in the case of complex inner product space. Let's now look at a finite dimensional real inner product space. So the field of scalars in this case is the real numbers. Inner product space. Then, okay, and T in L of V be a self-adjoint operator. Did I mention in the statement of the spectral theorem above that T is normal? Yes, it is. It is mentioned. Okay. So in this case, we are going to focus on T in L of V be a self-adjoint operator. Then there exists an orthonormal basis of V consisting of eigenvectors of. So in the case of a real inner product space, if you are given a self-adjoint operator, we do have that it is diagonalizable over R. So we have already done all the major work. So let us give a proof of this. The proof has already been done to a large extent already. The question would be, we will mimic the proof that we were trying to do in the case of normal operators. Where would be the hurdle that would come? So recall that again the proof can be done by induction on the dimension of V, which is equal to n. N is equal to 1. It is straightforward, is the same proof works. And let's assume that the theorem has been proved up to n minus 1. Now, if you are to mimic the proof of the spectral theorem for normal operators, we will be considering the characteristic polynomial, the characteristic polynomial of T. However, now we are in a real inner product space and we will not be able to say that the characteristic polynomial splits over real numbers in the general case. However, let me go back to a result from the previous lecture regarding the characteristic polynomial of self-adjoint operators. Yes, this is precisely the statement. So notice that if T is a self-adjoint operator on a finite dimensional inner product space, whether complex inner product space or real inner product space, in the case of complex inner product space, this theorem is redundant because anyway fundamental theorem of calculus, fundamental theorem of algebra tells us that the characteristic polynomial space. In the case of real inner products is where this is telling us a substantial amount of information. This tells us that it splits. Oh, I didn't actually mention over R, but that is understood. Here I didn't write over R because the statement was more general. It splits over the field of scalars. So if it was in the case of a complex inner product space, it splits over C. If it was in the case of a real inner product space, it splits over R. The proof did capture that. So yeah, I don't want to go through the proof again, but what it tells us is that splits over R because T is self-adjoint. So we'll use that information. Since T is self-adjoint, this is very important because it is self-adjoint, the characteristic polynomial of T splits over R. And let lambda 1 be a root of f of lambda. After this, the proof is extremely similar to what was done in the case of normal operator. So let V1 be an eigenvector corresponding to lambda 1. Let W be the span of V1 and consider W orthogonal. We notice that T and T star both are invariant. Sorry, W orthogonal is invariant under both T and T star, and by mimicking the proof for normal operators using the induction hypothesis, we get an orthonormal basis of V consisting of eigenvectors of T. So just say that I should go back to the proof of the spectral theorem for normal operators from the case when the induction hypothesis came into force. The proof is going to be exactly the same. Finally we will be getting hold of an orthonormal basis of V, which consists of eigenvectors of the self-adjoint operator T. And with that, that will be the proof, completion of the proof of the spectral theorem for the self-adjoint operators as well. So even though I did mention that the normal operators and self-adjoint operators are quite special, and many operators are not most operators don't turn out to be normal and self-adjoint. However, I should mention here that in real life there are many cases when the operators that we are studying does turn out to be normal and self-adjoint, normal and or self-adjoint. This is in fact true in physics many times, especially when you do, say for example, quantum mechanics. So the study of these operators is very useful and important, and the spectral theorem goes a long way in that front. So that's more or less everything that I would like to speak about spectral theorem. And with this, we have come to the conclusion of this particular course. I hope that you have enjoyed this course. I wish you all the luck and all the best for all your future endeavors. Thank you.